Dreams of cities on the moon or Mars are no longer just a fantasy, but tangible goals of ambitious projects, showing that the future of space colonization is closer than we think. In the race for colonization, spacecraft have been and remain the only link between Earth and new frontiers, the instruments of progress for understanding an almost infinitesimal part of the universe. Uncrewed spacecraft have advantages and disadvantages. They are controlled remotely or are autonomous and provide results back to Earth. One of the most important advantages is the absence of risk to human life, as there are no passengers on board. Of course, this means that missions can focus on research without concerns about crew safety. Space exploration using this type of spacecraft is less costly than manned missions. There are no political considerations in these missions, only scientific ones, eliminating concerns about geopolitical competition and allowing a focus on science. Another aspect is the reduction of the risk of contaminating potential sites with life is reduced because uncrewed spacecraft are easier to sterilize and do not carry human microorganisms. Additionally, they do not bring back anything they might find there. There is no need for human supplies such as food, oxygen, or water. They are more useful for collecting information from space, such as temperature, radiation, magnetic field, and the amount of water. They can withstand harsher atmospheric conditions, but they also have disadvantages. It is very difficult to repair an uncrewed spacecraft. It is difficult in Earth's orbit and impossible once it leaves orbit. If the uncrewed spacecraft fails, it means that parts of the mission afterward cannot be completed. For example, if a landing module, due to a malfunction in its anchoring system, lands in a shaded area of rocks, it will not be able to receive enough solar energy to recharge its batteries or even move out of the shadow. Since it operates in space, radio signals have a harder time reaching Earth, which delays the analysis time is delayed, and there are limited provisions for maintenance, which shortens the spacecraft's lifespan. A modern spacecraft, NASA's Orion spacecraft, is a key component of the Artemis program. NASA aims to return humans to the moon and establish a sustainable human presence on our natural satellite. Orion is designed as a multifunctional capsule that combines the latest technologies in propulsion, life support, and radiation protection. Consisting of the command and service module, it is capable of supporting a crew of up to 4 astronauts during long-duration space missions. The Orion command module is the pressurized part where the crew lives during the mission. It is designed to be reusable and serves as the astronauts' home and command center, equipped with the most advanced navigation and communication systems, as well as essential life support systems such as oxygen, water, and food. The service module contains the spacecraft's main propulsion and life support systems, including power generation. It is powered by large solar panels, which also provide thermal control for the spacecraft, essential for protecting the crew and sensitive equipment from extreme temperature variations in space. Orion is equipped with an Emergency Launch Abort System (LAS) that can quickly separate the command capsule from the booster in the event of an anomaly on the launch pad, or during the initial ascent, ensuring the crew's safety for a return to Earth. Orion is also equipped with a thermal shield, an advanced thermal shield capable of withstanding the extreme temperatures generated by re-entry into Earth's atmosphere at high speeds. The shield ensures that both the capsule and the crew land safely or splash down, using a sophisticated parachute system for the final deceleration. How a rocket flies. Scientists launch satellites and spacecraft into space. Every action has an equal and opposite reaction. This is the key idea behind how rockets work. If you watch images or videos of you will observe the expulsion of gases from the bottom of the rocket. The exhaust consists of flames, hot gases, and smoke, produced by the burning of the rocket's fuel, being pushed out from the rocket's engine toward the ground. This is the action force, and in response, the rocket begins to move in the opposite direction, which is the reaction force. Unfortunately, things are not simple. Earth's gravity still pulls the rocket downward. When a rocket burns fuel and expels exhaust, it generates an upward force called propulsion. However, to launch, it requires a lot of fuel, in such a way that the rocket is pushed upward with a force greater than the gravity pulling it down. A rocket must accelerate to at least 28,800 kilometers (h) and fly above much of the atmosphere on a curved trajectory around Earth to ensure that it won't be pulled back to the ground. As for orbit and how long it takes for a spacecraft to reach a planet, let's say you want to send a satellite into Earth's orbit. The process begins with the launch of a rocket, which, upon reaching a pre-established distance from Earth, will release the satellite into space. Once in orbit, the satellite continues to move thanks to the essential energy it received from the rocket, while Earth's gravity pulls it in a different direction. This interaction creates a dynamic balance that allows the satellite to remain in orbit around Earth. Interestingly, satellites closer to Earth are more strongly affected by gravity, which means they must move faster to avoid being pulled back to the surface. For example, the International Space Station, orbiting approximately 400 kilometers above Earth, not very far, as space begins roughly at 100 kilometers, travels at an impressive speed of 27,600 kilometers h. On the other hand, satellites farther from Earth, such as those used for tracking and data relay, orbit at 35,400 kilometers or more. At this distance, Earth's gravitational pull is weaker, allowing them to maintain a stable orbit. To achieve this, you would need to accelerate to approximately 400 kilometers h. For example, Mars and Earth reach their closest distance to each other approximately every 2 years. It is essential to launch the rocket at the right time to ensure the spacecraft and Mars arrive at the same location simultaneously, as time is crucial. The time required for a spacecraft to reach a planet depends on many factors: distance, speed, chosen trajectory, whether gravitational assistance is used, and whether the spacecraft has a human crew or not. For instance, the Moon is 384,400 kilometers away from Earth. The Apollo 11 mission lasted 8 days, 3 hours, and 18 minutes. The distance to Mars, however, varies between approximately 54.6 million kilometers and 401 million km, significant range. Recent robotic missions, such as NASA's Perseverance, took 7 months to reach Mars. Venus is about 41 million kilometers away, and missions to Venus, like the European Space Agency's Venus Express, took 5 months. Missions to the outer solar system take much longer. For example, NASA's Juno spacecraft took nearly 5 years to reach Jupiter, while Voyager took 12 years to reach Neptune, a journey to another solar system, such as Proxima Centauri's closest star to the Sun, remains beyond the realm of imagination at 4.2 light-years away. With current technology, humans leaving Earth would no longer be the same species by the time they arrived, as the trip would take tens of thousands of years. Travel times in space could decrease significantly with advancements in propulsion technology, such as nuclear thermal and electric propulsion, innovations that could make future missions faster than those of today. Speaking of Newton earlier, who are the other individuals who made space travel possible? The field of spacecraft technology has been shaped by numerous figures from different eras and places. For instance, Konstantin Eduardovich Tsiolkovsky was born in Russia. A self-taught scientist, he made significant contributions to rocketry and space exploration despite living most of his life in isolation and being nearly deaf. He is best known for deriving the rocket equation, known as Tsiolkovsky's equation, which calculates the final velocity of a rocket by accounting for its initial mass, final mass, and exhaust gas velocity. Robert Goddard, an American engineer, professor, physicist, and inventor, is credited with designing and building the world's first liquid-fueled rocket. He successfully launched it on March 16, 1926, nearly 100 years ago. Hermann Oberth, a Hungarian-German engineer, published the work The Rocket into Planetary Space in 1923. He detailed the possibility of using rockets to reach space in that work, which was followed by the more comprehensive Ways to Space navigation in 1929. This later publication provided detailed calculations and concepts for spaceflight, including propulsion techniques, the effects of microgravity on the human body, and the use of rockets for interplanetary exploration. Wernher von Braun, a German aerospace engineer and space architect, was one of the most significant figures in the development of rocket technology in both Germany and America. He was the chief architect of the Saturn V launch vehicle, the key component that enabled the Apollo missions to reach the Moon. Sergei Korolev was the chief architect of the Soviet space program, responsible for launching the world's first artificial satellite, Sputnik, and for the first human spaceflight carried out by Yuri Gagarin. His involvement was crucial in establishing the Soviet Union as a major, if not the leading, player in the space race. Yuri Gagarin, a Soviet pilot and the first cosmonaut, made history as the first human to travel into space. This brings us to the difference between cosmonaut and astronaut. We often use both terms interchangeably for their historical contexts, but traditionally, the East Soviet Union used cosmonaut while the West used astronaut. Gagarin was launched aboard the Vostok 1 spacecraft and completed one full orbit around Earth. Valentina Tereshkova, who is still alive, was a Soviet cosmonaut and the first woman to fly into space. She piloted Vostok 6 on June 16, 1963, and during her mission, she orbited Earth 48 times. On a journey that lasted 3 days, nearly 71 hours, Neil Armstrong was the American astronaut and the first person to land on the moon on July 20, 1969, during the Apollo 11 mission. How a rocket is built. The structural system. This serves as the skeleton of the rocket, designed to withstand the stresses of launch and flight while remaining as lightweight as possible. It includes the rocket's body, which houses other components, as well as the payload compartment used to transport satellites, instruments, and crew capsules. The propulsion system. This system powers the rocket by generating the thrust needed to overcome Earth's gravity. It comprises engines that use a combination of fuel and an oxidizer, which can be in solid, liquid, or hybrid forms. It includes the engines that provide the thrust necessary to escape Earth's gravity. This system uses a combination of fuel and oxidizer, which can be solid, liquid, or hybrid. The choice of propulsion system affects the power, efficiency, and reliability of the rocket. The guidance system is responsible for controlling the rocket's flight direction, ensuring the trajectory is followed. It includes onboard computers, sensors, and navigation equipment. The guidance system adjusts the rocket's engines and aerodynamic surfaces to maintain the correct path. To maintain the correct trajectory, the payload is what the rocket carries into space. This can range from satellites to scientific instruments, planetary exploration robots, or human-crewed spacecraft. The rocket's design must adapt to the specific needs of the payload, including protection from the harsh environment of space. Many rockets are designed with multiple stages to efficiently reach space. Each stage has its own engines and fuel reserves, with parts that are discarded when the fuel is depleted, reducing the mass that the remaining parts of the rocket need to carry. This design allows for more efficient fuel use and the achievement of higher speeds. However, modern rockets are often designed to be reusable, delivering the payload and then returning to Earth. Spacecraft re-entering Earth's atmosphere or operating near the Sun require heat protection to withstand extreme temperatures. The thermal protection system includes thermal shields and insulation to protect the payload and sensitive components from the intense heat generated during re-entry or solar proximity. The electrical system includes power sources, such as batteries or solar panels, cables, and electronic devices, all essential for controlling the rocket, communicating with Earth, and operating onboard instruments. Additionally, there is the life support system. If there are people on board, it manages water, food, and air, handles waste, and maintains a habitable environment within the spacecraft. How does an artificial satellite work? An artificial satellite is a man-made object intentionally placed into orbit around Earth or another celestial body. A satellite is launched into space by a rocket and placed on a specific orbit based on its purpose. The most common orbits are low Earth orbit LEO, medium Earth orbit MEO, and high Earth orbit HAO. You might have meant to say geostationary orbit and polar orbit. Once on orbit, the satellite must maintain its trajectory. It does this by balancing gravitational forces with its speed. Some satellites have onboard propulsion systems to make adjustments and counteract any influence from atmospheric drag or gravitational pull from other celestial bodies, not just Earth. Everything in space and the moon exerts a gravitational pull. Most satellites use solar panels to convert sunlight into electricity, and batteries store energy for use during periods when the satellite is in the Earth's shadow and not receiving sunlight. Satellites communicate with ground stations via radio waves, receiving commands and sending data back to Earth. Antennas are used to transmit and receive signals, and the design and orientation of the antenna are very important for efficient communication, especially for satellites in geostationary orbit, to maintain a constant connection with a ground station. Satellites are equipped with onboard computers that process commands from Earth and manage the satellite systems, including navigation, power, and payload operations. Gyroscopes and reaction wheels can be used to control the satellite's orientation in space, ensuring that instruments and solar panels are properly positioned. The payload is specific equipment for the satellite's mission, which could include cameras for observing Earth or another planet, sensors for scientific measurements, communication devices, or navigation instruments. Space can be extremely cold in Earth's shadow and very hot in direct sunlight. Satellites use thermal blankets to protect themselves. Heaters and radiators are used to regulate temperature and protect sensitive equipment. Once on orbit, the satellite operates autonomously based on pre-programmed instructions and real-time commands from ground control. If needed, satellites collect and transmit data, perform their functions, and adjust their orbit or orientation as required. The satellite is tracked from the ground by stations worldwide, which receive and send data and commands further. Satellites are used for weather forecasting, GPS navigation, global communications, and space exploration. They have a significant, tangible impact on our daily lives, as well as on scientific understanding. Classification of spacecraft. Flying spacecraft sent to fly past a celestial body without entering orbit around it are used for quick observations and data collection. Orbital spacecraft are designed to enter and remain in orbit around a celestial body, such as a planet, star, or asteroid. Quite large. They are used to perform detailed observations and to map the surface and properties of the studied object. Atmospheric spacecraft are designed to study the atmosphere of a celestial body, such as planets with atmospheres or natural satellites. They may be designed to enter its atmosphere to perform direct measurements or to conduct remote observations. Landing spacecraft are used for direct field research to collect samples and data from the surface of the celestial body. Penetrators are designed to penetrate the surface of the celestial body to take measurements, explore the subsurface, and study the composition and internal characteristics of the planet or celestial body. There are also rover spacecraft robotic machines that transport vehicles on the surface of a celestial body. They are used to explore the terrain, conduct experiments, and perform research at multiple locations on the planet's surface. We also have spacecraft for observation. Here, there are advanced observation instruments, telescopes, and sensors for making astronomical observations in outer space. Hubble is one such instrument. Communication and navigation spacecraft are used to facilitate contact between other spacecraft, or between spacecraft and ground stations on Earth. We are talking about satellites or navigation systems like GPS. What happens on the International Space Station? It is a research laboratory and a living space. In low Earth orbit, I don't know how this episode will age, because currently it is losing atmosphere. Nothing is set in stone regarding what will happen to the poor space station, which is almost 30 years old and should be replaced. However, it's very expensive to replace it. Here, astronauts from various countries around the world live, conducting experiments and scientific research, testing new technologies. They perform experiments in a wide range of fields, such as chemistry, physics, astronomy, materials science, and biology. It's a great testing ground for demonstrating new technologies and systems that could be used in future space exploration missions. We have made progress in life support systems, propulsion, communication, and spacecraft design. Astronauts participate in medical experiments to study the effects of long-duration space flights on the human body. These studies help scientists better understand the physiological changes that occur in space and develop countermeasures to reduce potential risks to the health of future astronauts. The station provides an observation point to monitor the Earth's surrounding environment for natural disasters and the effects of climate change. It serves as an educational platform to inspire and train students from all over the world in science, technology, engineering, and mathematics. We have educational programs, experiments, and demonstrations, and astronauts often interact with students through live video calls and informational events. It is a collaborative effort involving space agencies from multiple countries: NASA from the United States, Roscosmos from Russia, ESA from Europe, JAXA from Japan, and CSA from Canada. Now, we come to the more intriguing part: space weapons. Space weapons refer to systems or technologies developed and deployed in space with the goal of providing military advantages, such as direct air, sea, or land attacks, neutralizing or destroying satellites and other hostile space assets. These can include a variety of technologies, from satellites equipped with weapons to systems designed to destroy or interfere with the satellites of other countries in orbit. The term space weapons can also encompass anti-satellite technologies, space lasers, orbital bombardment systems like projectiles that can be launched from space to Earth, and platforms for launching or guiding conventional weapons. Space weapons may offer unique surveillance and reconnaissance capabilities, providing valuable information about the movements and intentions of adversaries. They can enhance decision-making in real time during military operations. The presence and capability of space weapons can act as a deterrent against aggression or hostile actions, functioning as a sort of surveillance system from space. The mere possibility of a rapid and devastating response is believed to prevent conflicts. In the digital age, satellites play a significant role in communication, navigation, and environmental monitoring. Investments in military space technology can stimulate innovation and development in the technological sectors. Due to these consequences, several countries have opposed any future ASAT tests. The future of space travel is at a fascinating moment, with advancements in technology, growing interest from private companies, and international collaboration shaping a new era of space exploration and utilization. There are some key trends and projections for the future of space travel. We have SpaceX, Blue Origin, and Virgin Galactic contributing to reducing the cost of access to space through reusable rocket technology and other innovations. This trend is expected to continue, opening up new opportunities for space tourism, commercial space stations, and even private missions to the moon. How about going on vacation to the moon? The spread of small satellites and the development of space infrastructure, such as satellite internet constellations like SpaceX's Starlink, is transforming global communication networks and Earth observation capabilities. Suborbital short-duration flights and space tourism are becoming more tangible. The cost is high, talking millions, but there's an audience for it, and it could become more popular as costs decrease over time. NASA's Artemis program, together with international and private partners, aims to send humans back to the moon and establish a continuous human presence. We also have the idea of extracting lunar resources, such as ice, which can be converted into rocket fuel through electrolysis, a critical step for establishing an economy and supporting deep space exploration. NASA, SpaceX, and other companies are focusing on Mars, with ambitious plans to send humans to the Red Planet. They've been talking about the 2030s, but those years are just around the corner. These missions will require significant advancements in life support systems, propulsion technology, and strategies for long-duration space travel. Missions to the outer solar system could become more common. We may explore Jupiter's moons, such as Europa and Saturn's Enceladus, which have potential subsurface oceans, where, if there is water, there could also be life, and that is what we hope to find there. Research into new propulsion methods, like thermal-nuclear and electric propulsion, could significantly reduce travel time in the solar system, making distant planets and asteroids more accessible. Developing technologies for long-term habitation in space, closed-loop life support systems, and space agriculture are things we'll need to solve if we want to sustain human life on another planet. As space becomes more accessible, it also becomes more crowded. International collaboration and the development of space laws will be necessary to manage traffic, protect space assets, and ensure the peaceful use of outer space. What are the safety measures on space shuttles? There are critical systems with redundant elements to ensure that if one system fails, another takes its place. But these systems are designed by brilliant people, not like on the phone. This redundancy applies to systems such as propulsion, communication, and energy generation. Before launch, extensive tests and inspections are performed to verify that the spacecraft and components function perfectly and can withstand the journey. More recently, the Chinese lost a rocket due to an error during the launch mechanism test. They accidentally launched it. This still happens today. Launch escape systems are also implemented to allow astronauts to abandon the mission in an emergency. It's not like it used to be, where you just go on a whim. Modern spacecraft are equipped with vital support systems that regulate temperature and humidity, eliminate carbon dioxide, and are 91% efficient when it comes to water reuse. These systems are closely monitored to ensure they work correctly throughout the mission. They also have shielding to protect astronauts from harmful space radiation, cosmic rays, and solar radiation. Astronauts are not picked up off the street or taken from oil rigs. They are people trained for a lifetime, rigorously preparing their bodies for the effects of microgravity, muscle atrophy, bone density loss, and fluid redistribution. Spacecraft are equipped with sensors and systems, to detect and avoid collisions with other objects in space, such as debris or other spacecraft. Mission planners closely monitor spacecraft trajectories to minimize the risk of collision. Before re-entering Earth's atmosphere, spacecraft undergo thorough checks to ensure they can safely re-enter and land. Parachutes, thermal shields, and other systems are used to slow the spacecraft and protect both the vehicle and the crew. The Mission Control Center oversees everything. The shuttle, the rocket, the station, everything is supervised and coordinated. These are rockets, space shuttles, and satellites in brief. I hope you enjoyed this episode. If you liked it, please give a like, leave a comment, and we'll make more detailed episodes about each element. Thank you for your attention. Don't forget to share, like, and subscribe.